41,000 years ago, Earth entered one of the strangest episodes in its recent history. The magnetic field that usually shields our planet from cosmic and solar radiation began to weaken and wander. The poles shifted erratically across thousands of miles, and for a brief span, just a few centuries within a 2,000-year disruption, the field's strength collapsed to less than 10% of what it is today. This event, known as the Laschamps Excursion, transformed the skies above Earth, altered the chemistry of the atmosphere, and left our ancestors to face dazzling yet dangerous conditions. To understand why this mattered, consider the role of Earth's magnetic field. Normally, it behaves like a giant bar magnet, aligned roughly with the planet's rotational axis, channeling charged particles toward the poles and creating the familiar auroral ovals in high latitudes. But during the Laschamps Excursion, the dipole broke apart into several weaker poles scattered across the globe. Without a strong magnetic shield, more cosmic rays and solar particles bombarded the atmosphere. Auroras likely appeared not just in polar skies, but as far south as the tropics, turning the heavens into a canvas of shifting green and red light visible to nearly everyone alive at the time. These changes were not simply visual spectacles. When more high-energy particles penetrate the upper atmosphere, they disrupt its chemistry. Ionization increases, producing reactive nitrogen and hydrogen oxides that can destroy ozone. With less ozone, more ultraviolet B radiation can reach the surface, particularly during episodes of intense solar activity. Although the magnetosphere does not directly block ultraviolet light, ozone does. Its weakening can indirectly raise UV levels by letting more particles drive chemical reactions. Modern models suggest that under Laschamps-like conditions, solar storms could have caused significant, though regionally variable, surges of surface UVB. How do we know all of this happened tens of thousands of years ago? The evidence comes from several natural archives. Lava flows and sediment layers preserve the orientation and strength of Earth's magnetic field when they cooled or settled, confirming the sharp dip in field intensity around 41,000 years ago. Ice cores from Greenland and Antarctica, record spikes in cosmogenic isotopes such as beryllium-10 and chlorine-36, produced when cosmic rays strike the atmosphere. Even more precise are the radiocarbon signals locked in the rings of ancient kauri trees from New Zealand. These trees captured an extraordinary surge in carbon-14, marking the peak of cosmic ray bombardment at the very moment when the field was weakest. Together, these proxies give us a detailed picture, a chaotic, fractured field lasting nearly 2 millennia, with a particularly weak phase that endured for several hundred years. What did this mean for humans on the ground? Both Homo sapiens and Neanderthals were present in Europe during the Laschamps Excursion. Archaeological evidence suggests that people adopted strategies that may have offered protection against the new risks. Cave occupation seems to have increased, providing natural shielding from both radiation and weather extremes. Around this time, evidence for tailored clothing appears in the form of bone needles, suggesting that people were investing more in fitted garments that covered the skin more effectively. Most intriguingly, the use of ochre pigment intensified. Ochre, an iron-rich mineral, has been shown in experiments to provide measurable photoprotection when applied to skin. It may have served as one of the earliest sunscreens, blending practical defense with symbolic or ritual significance. These adaptations were not universal or uniform. Different populations responded in different ways, shaped also by climate variability, migration, and cultural practices. It would be simplistic to claim that the Laschamps Excursion alone caused major evolutionary or demographic shifts, such as the disappearance of Neanderthals. But it is increasingly clear that space weather and geomagnetic changes formed part of the environmental pressures to which humans had to respond. The broader context of this time adds more complexity. The world was in the grip of the last ice age, with glaciers expanding and contracting in response to shifting climates. Around 40,000 years ago, humans were spreading across Eurasia, experimenting with new tools, art, and cultural expressions. Neanderthals were in decline, though their final disappearance likely involved many factors: competition with modern humans, climatic instability, demographic fragility, and perhaps stresses such as increased radiation exposure. In Australia, debates continue about whether megafaunal extinctions align with this period, but evidence suggests they began earlier and were shaped more by human hunting and environmental change than by geomagnetic disruption. For us today, the Laschamps Excursion offers both a window into the deep past and a warning for the future. Magnetic excursions are not rare in geological terms. They have happened before and will happen again. If another occurred in our time, humanity would not face the same direct biological risks as our Paleolithic ancestors. We have sunscreen, shelters, and medicine. But our technologies would be vulnerable. Satellites, navigation systems, power grids, and aviation routes all depend on a stable space weather environment. A severely weakened magnetic field would magnify the effects of solar storms, creating disruptions far more consequential than a sunburn. The lesson from 41,000 years ago is that space weather has always reached into the human realm. When the shield above faltered, people adapted, with caves, clothing, and minerals from the Earth itself. They survived by weaving cosmic events into the fabric of daily life. Understanding their story helps us prepare for the next time Earth's magnetic cloak begins to slip, reminding us that even the vastness of space is deeply connected to the way we live on the ground.